Right, good afternoon, good morning, good evening, wherever you are for this second GO2NE webinar. Just see the number of attendees is still increasing, so people are logging on. We wait 1 or 2 more minutes before we start. I hope you are in the right place and look forward to this event. All right, so let us start. Welcome everybody to this second webinar on ocean oxygen processes deoxygenation. We are organized by the Global Ocean Oxygen Network and IOC. We are very glad to have 2 eminent speakers today again, and to have a huge audience. Thanks everybody for connecting. Before we start, just a message: this meeting will be recorded and we plan to put the recording online afterwards. So if you do not wish that your comments, if you have them, your question is recorded or is included in this document, let us know, please, so then we will edit it. Otherwise, it will appear sometime for those who can't make it today to view the event. We start with the another procedural issue. You are all, except for the speakers and the organizers, you're all muted. And so please enter your questions that you hopefully will have into the questions box on the right of your screen, where I will then repeat them to the speakers after the talks. We have 2 talks, each 20 minutes, and 10-minute question and answer slot thereafter. And we start with our first speaker. That's Sören Thomsen. He studied oceanography in Kiel and in Hamburg on turbulence theory and measurements of turbulence in the ocean. He then moved on to a PhD and was actually during his PhD already a co-PI on a sub-project on our collaborative research center on ocean oxygen in the tropical oceans. And he got a Marie Curie fellowship to move to Paris after his PhD, and where he's now at LOCEAN and doing a postdoc right now. And well, he has interests in all kinds of different methods to explore the ocean, and he is really well prepared to use theory, modeling, and field measurements to study meso, submeso, and microscale processes in the ocean. And that's also the topic of his talk today, the impacts of small-scale processes in the oxygen minimum zone of Peru on the dynamics and the patterns of oxygen in that region. Thanks, Sören, for being here, and I look forward to your talk.
So, thank you, Andreas. Can you see the screen?
Yes, that's fine now.
Okay, so thanks a lot, Andreas, for this nice introduction, and thanks for the organizers for inviting me to this nice webinar series. And of course, I also want to thank all my collaborators and co-authors over the last year in Kiel and in Paris. And as Andreas said, today I will talk about how do fine-scale physical processes shape the oxycline of Peru. So let's start. Eastern boundary upwelling systems are these regions of the eastern part of the oceans which are forced by longshore winds, which then drives the water offshore, and then this water is replaced by cold and nutrient-rich water from below. This water is also typically very low in oxygen, and although these regions just account for 1% of the ocean surface, 20% of the fish is actually caught there. And this is why they are so important for the society, for the people living around these coasts. However, these regions are also impacted by climate change. And there are multiple stressors. There are changes in the wind forcing. There's ocean heating and increased stratification. But there's also deoxygenation, what we talked today about, or in this webinar series in general. And there's ocean acidification. And what you can see here is for measurements of California, which is probably the best sampled upwelling system, where you can see just recently, in the last 15 years, that suddenly anoxic events occurred at the coast, which you can see here in red with these measurements. So that shows that these kind of changes can be quite rapid and nonlinear. And it's very important that we understand what drives these changes. And so, but if we look into, say, the best models we have available and try to make future projections, for example, here, for the oxycline depths of Peru, the oxycline is the depth which separates the highly oxygenated water from the surface and the low or zero oxygen water from below. So you can see here, for example, that some models agree quite well with the observed oxycline depths and project not a huge change, and another is a little bit more biased and also doesn't change, and another one shows a huge decline. In general, the state-of-the-art projections for Peru and other upwelling systems strongly diverge, particularly in the biogeochemical properties like nitrate or oxygen. So this is due to global issues we have with this model, but also local processes. So here I will today talk about the role of local and fine-scale processes for the shape of this oxycline. So first of all, I will talk a little bit about how does upwelling work, and particularly focus on the role of this fine-scale process for upwelling in general. And then I will relate that to oxygen and what it means for the oxycline depths of Peru. So we probably all know the typical wind-driven upwelling process. The wind blows along the coast, push this warm water offshore, and then this warm water has to be replaced by cold, nutrient-rich and low oxygen water from below. However, the upwelling systems are much more complex, and we have these so-called eddies. So these systems are highly variable. Eddies are structures which are rotating around and can have a few kilometers to 100-kilometer scale. And these processes are very important because they transport water properties in the horizontal, but also in the vertical. And for example, these processes reduce the productivity, for example, in upwelling systems, which has been shown in various studies, and you can have a look in the literature here below. But today we want to talk about oxygen. Then there's another very important process, which I call here diffusive upwelling, which mainly makes, in the ocean, we also have so-called internal waves. This is when you have your coffee pot and you have warmer milk above or colder coffee below, and then there's this wave inside. And if you mix it, so when this wave create turbulence and 2 centimeter scales, and then the milk is diffusing and you have the same color. So this turbulence is actually very important also because it drives vertical fluxes of some different tracers, for example, oxygen. And so we have to understand all these different processes if we want to understand upwelling systems. So how do these processes now shape the oxycline of Peru? So during my PhD, we went to Peru and we deployed quite a number of ocean gliders, which are autonomous platforms. And we were there at the same time with the research vessel. And we were lucky because one of these eddies was formed during that month, or there were 2 months actually. And you can see this rotating structure here. And on the right, you see the subsurface velocity structure of this eddy. And so you can see that it's about a few 100 kilometers huge, and they rotate around water. And what this causes is that you can see on the lower left, the velocities are changing due to these eddies, and then the high oxygen water from offshore is actually transported towards the coast. And you can see that after the eddy passed or moved away, you can see here with the red arrow that the region was highly oxygenated after this eddy was formed there. Also, these eddies transport very low oxygen very far offshore and play also the important role of the overall shape of the whole oxygen minimum zones. So then we wanted to look into finer scale processes, so-called sub-mesoscale processes. These processes are acting at a few kilometer scales, and very typical phenomena are so-called filaments, which you can see here in the SST, observed by satellites. And we were quite lucky that one of our gliders also passed through this filament several times. And what we could see is that in this filament, the water, which is just newly upwelled, is actually already highly oxygenated, and then it's subducted back into the thermocline. And so this was actually the first observational evidence that oxygen is subducted in the structures of Peru. And then we were thinking probably, or maybe this is a very important process, so we thought we should investigate this further. And luckily, Jart Hauschild, who is now doing his PhD, with Andreas and myself and Vincent and others from France, he looked into that in a high-resolution coupled physical biogeochemical model. So what he found is that if you include these processes, indeed, you deepen the oxycline quite significantly here. These are preliminary results of 30 micromole per liter if you include these kind of processes. So they are quite important. Then, last but not least, what you can see here is the turbulence profiler. So this one you use to observe the so-called diffusive upwelling. And there are very small sensors in the front which observe very small scale turbulent fluctuations. And if you do that at the same time with observing oxygen, you can quantify this so-called diffusive oxygen flux. And what we could show is that actually the diffusive oxygen supply is comparable to the local oxygen consumption from the magnitude which was observed by other here Kalvelager et al. And so it's about 1 micromole per kilogram per day, actually. So that means you definitely have to account for this diffusive oxygen fluxes if you want to properly represent oxygen dynamics near the coast or in the upwelling systems. So in summary, we come already to the summary. Upwelling systems are highly variable. And beside the classical wind-driven upwelling systems, we have fine-scale processes like eddies, filaments, small-scale turbulence, and they're very important to transport properties like temperature, oxygen, nutrients, and so on. And we definitely have to account for them if we want to understand how these systems are going to behave in the future. And for oxygen, eddies are regularly formed of Peru, and they ventilate the oxycline and by horizontal mixing, and they also transport low oxygen waters far offshore. The upwelled oxygenated water is then also subducted in these so-called filaments. And the modeling study now continued by Jart confirms these submesoscale processes actually very important. And so we are looking forward on what he will find out in the future. And the observed diffusive vertical oxygen flux through this very small scale turbulence are actually comparable to the oxygen consumption. So you cannot neglect these kind of processes in your oxygen budget. And this brings me to some kind of outlook. What I think what we should maybe do as a community is, because we want to understand how oxygen is changing at local scale or regional scale. And so this means we want to know how the oxygen is changing very close to the coast. So we should connect these global models much better with the local models, for example, by multi-scale downscaling modeling or other approaches to really understand what's happening at the coast, because this is what is important for society. And I think we will resolve horizontal scales of a few kilometers, or they already resolved in some models. So because the computing power will continue to increase over the next years, but this turbulent diffusive upwelling, which will remain a very important challenge. So we should put our focus on that, and especially looking on how this diffusive upwelling is actually, how is it happening in state-of-the-art models? How can we improve it and better parameterize it, and understand also the impact, for example, of changing strategy on the fluxes. So I want to thank everyone for following this webinar. And here you will have the slides with the references. And I want to also say a few words about the pandemic and virtual conferences. So I'm very happy that we are now exchanging online, and because it's very inclusive and has a lot of other co-benefits. But let's keep in mind that we needed, as a whole scientific community, a deadly virus to do this. And I think this is very important to keep in mind. And we know since a long time, or others, that this virtual community is very powerful, and it's very. So I really hope that we will stay virtual after this pandemic and keep exchanging inclusive and sustainable. because I think that's how we should go on in the future. Thank you.
Thank you very much, Sören, also for this well, highly motivated talk and exciting talk, and your quest for staying online, using online communication tools as we try to do here. If you have any questions, please type them into the questions box so that I can see them and repeat everything to Sören. Well, you showed, Sören, that the effects of steering, lateral eddy-induced transport, and the downward diffusive microscale transport of oxygen. So yes, the mesoscale and the microscale transport, and both seem to, well, both act to bring oxygen into the ocean interior. There's also the residual overturning, the eddy-induced driven overturning that tends to oppose the general large-scale upwelling circulation. Do you think that is important in bringing oxygen down as well, or does it? Is there any evidence for a slowdown of the wind-driven overturning by eddy activity?
Oh, you mean on global scale?
Yes, or in the upwelling region, if you have the like an overturning circulation driven by eddies, which would be induced downwelling along the coast.
Well, I haven't studied that. I mean, in principle, most of my work has not focused so much on long-term changes, so I'm careful in answering that. And if people in the audience know better, maybe they can post that in some comments on that in the chat. What I know is that, of course, when the wind is changing, you're also changing the strength of the eddies, and this can also balance, or this can cancel out each other. So, for example, we know that from the Southern Ocean, for example, if you have changes in the wind forcing, then you also have the eddies also become stronger, and then they stronger counteract this upwelling, for example, the overturning. So that could also be happening in the upwelling systems when we, for example, have increasing or decreasing winds. I'm not sure that answered your question.
Yes, I wonder whether there's any difference in the upwelling and eddy resolving and non-eddy resolving models, whether one can see that, and whether any parameterization that takes into account for eddy-induced residual mean circulation is needed.
Well, I mean, the Ekman or the Ekman upwelling is wind force, but the residual, of course, depends on the eddy strength. So it depends on how much you resolve it, I would say. And in the end, important is, of course, are the buoyancy fluxes and the internal mixing, which will then determine your residual. Yes. So that's important to look at, yes.
That was the second question, partly answered. I think the source of the eddy activity or the energy that goes into eddies, is it possible to say how much comes from the local wind forcing and how much comes from potential energy driven by the mean upwelling?
Well, it's possible to do that. I haven't done that for Peru. I did some work on baroclinic instability in the Labrador Current, but of Peru, for example, the eddy I showed there was formed by so-called flow separation. That's what we hypothesize. Is that we have the undercurrent, and then when this undercurrent is actually going to some areas where there's very sharp changes in the topography, this forces the current to overshoot. So this is more barotropic instability type. But of course, the upwelling front itself can also become very clinically unstable and form eddies more than near the surface. And there's a nice study by Colas et al. To look into that into detail.
Okay. And then there's a question by Marie-Laure Grégoire. How do you expect that new satellite products will improve the understanding of the impact of eddies on deoxygenation? And
on deoxygenation.
Yes. Or what kind of satellite data would be most useful?
I think I've not worked a lot with satellite data, but I think we used a lot of the satellite. I mean, for my kind of work, we used a lot of the satellite data to plan actually our process studies and to look before where are typically filaments formed, for example. And that's why we were also in the end lucky, I guess, to find this filament where we were looking for. So that's very nice to have. And on the same time, when we were there on the ship, we were constantly using these satellites and using their this instantaneous SST measurements, for example, to plan our observations and adapt them in real time. But for the eddies, you can, it's a little bit difficult, so you have to be careful there whether the coast is influencing the measurement. But in principle, you can quantify the eddy kinetic energy. The problem with the eddy I showed is that it's subsurface eddy, and you could not see it with the satellite actually. And they are very common off Peru, these subsurface eddies. So that's something you have to keep in mind. You can sometimes see them in the SST or in other parameters, but not that good in the SSH.
And there's a question from Mark Wells. Can you comment on how fine-scale processes may influence vertical diffusive flux rates and their variability? Is that a continuous background, or does it?
So I mean, in principle, I assume that, I mean, I'm not sure which, fine scale in principle is defined as a very scale before this micro scale, but if, I mean, the meso and the sub-meso scale are also influencing, of course, this microscale fluxes or this turbulence. But I think of Peru, the most important are really at the coast due to the breaking of internal waves related to tides. My question. So what I think is more important is to look at how stratification is changing and how that actually impacts then this diffusive flux. I don't expect that all the other driver, like the tides or the sub-meso scale, will change so significantly, but the stratification will change, and this will impact all the other processes.
There was one question about double diffusion. Does it play any role, or is it mostly breaking internal waves and shear instability?
I want to say something wrong, but I think it's not that important of Peru because it's very highly variable systems.
Mm-hmm. The question, well, by Giorgio Dall'Olmo, is it? Do you think it's important to quantify respiration and what?
Yes.
How it depends on environmental parameters?
Yes, I think that it's very important to quantify the consumption or the respiration. And I mean, we had some values here from Kalberlager and so on. Of course, it's very difficult to quantify this really well, but I think that's something very important because then this is something we should then compare also in the models, because it's, I mean, one of the key parts of the budget, and it constrains a lot of the other parameters too. So I think that's, yes, we should measure this better, or try to have, yeah.
Yes. What would be a good measurement method, and how would you account for zooplankton respiration?
Well, I'm not an expert on how to measure consumption. I just looked at it, how the other groups did that on the ship, and I just heard important is that you, for example, if you take water into a bottle, that you do that very quick and just very short, just for 1 or 2 hours or so, and then see how the oxygen goes down. The zooplankton, I think, in Rainer Kiko did great work on that. So he took some zooplankton and then he isolated them into a small bottle, and on the single zooplankton level quantify, or this group collaborators quantified how much CO2 oxygen is consumed, and then they use this UVP to quantify the numbers of zooplankton, like different zooplankton species, and then they could scale that up, these kind of values. I think that's a quite good approach.
Yes, thank you. And do you have any evidence, that's Karen Wishner asked this, about whether the mesoscale and submesoscale features move zooplankton around in a way that has then effects on oxygen consumption again, so that the concentrating mechanisms?
Well, I have not studied that, but that's a great opportunity to give a I'm not sure. I think tomorrow there's an EBUS webinar, and I think it's because we talk about meso and submesoscale process, how they impact fine scale mixing. But I also read something on phytoplankton, zooplankton. So maybe there would be some more information that I.
By Nicolas Maillot. Yeah.
So it's very likely that they transport around because it's quite strong current. So it's just that I didn't study that.
Yeah. The last question I would like to, if there were many more questions, we will send them to you later, and you can then reply to those, ask them the questions by.
Okay.
But one here relevant also for the next talk. Do you think meso and submesoscale processes in the upwelling regions are only specifically relevant for regional concerns, or also for oxygen dynamics at a global scale?
I think when I started my PhD, the submesoscale was, really quite a lot of work done in the US, but it was still like somehow starting. And in the beginning, people were focusing on some different regions where this process occur, but I think we now know that they are basically everywhere. So when I think for everything where you have surface fluxes, exchange and communication between surface and interior, they are very important on all kind of timescales, especially for the fluxes and the flux variability.
Okay, thank you. And the global oxygen budget, didn't get that. Do you think it's...
Maybe after the second talk we can repeat this question.
Okay.
I'm really not working on global scale so much, but I know that for other parameters like temperatures, we have temperature in the Southern Ocean, we have seen huge changes if submesoscales are either explicitly resolved or parametrized.
Mm-hmm.
So it's very likely that they also impact oxygen because
thank you very much.
Okay.
Yeah, sorry, there's a couple of many more questions here which we can't address all. I try to pick out those that were most complementary and diverse. Not sure whether I was very successful, but we will send you the list, and then you have a chance to address all of them. And if people have more questions, please send them in via the questions box here. We will collect them and distribute them, and ensure that Sören has a chance to answer everything and get in contact with you. Yes. That's the first half of our webinar. Thank you very much, Sören, for this excellent presentation, and also for your efforts in stimulating exchange in these difficult times, and moving science forward, and also giving opportunities to particularly early career scientists to get involved, get in contact, and jointly move science and our environment forward.
Yeah. Thank you.
This brings me to our second speaker today, Laure Resplandy. Laure is a marine biogeochemist. She studied in Paris. She's using ocean models using and developing models and to address global change, carbon cycle. Then when moving on to postdocs in Southampton and Scripps, also looking at ocean acidification, deoxygenation. And she always, besides being a modeler, well, I know her as a modeler, she is very connected to the ground truth, looking at data in the atmosphere and the ocean, and making really sense of both elements, real observations and theoretical concepts coded up in models. She's now an assistant professor at University of Princeton and recently got a very prestigious Sloan Foundation Research Award. And I'm very glad that we can have her here today to expand, hopefully, on Sören's excellent introduction and overview of our regional scale processes and present us a figure of the global perspective. Will oxygen minimum zones expand or shrink in the future? Thanks very much, Laure, and I look forward to your presentation.
Thank you, Andreas, and thank you to the organizer for that webinar. So I'm going to talk about oxygen minimum zones and maybe going. Sören was looking at a small portion here in Peru, and what I hope to give here is a more global perspective. But I will have a focus on the Pacific also, which is the largest OMZ. And what I would like to talk about is how are they going to change in the future? Are they going to expand or not? And I'm going to be focusing on specifically on the role of ocean mixing and biogeochemical feedbacks. So oxygen minimum zones are those, when I talk about oxygen minimum zones here, are those like red areas with low oxygen values at intermediate depth of about 80, 100 micromolar. And so as the ocean warms, it loses oxygen, and that's what we call global deoxygenation. And here is a map of those observed change in oxygen since the 60s, where you see most red in many parts of the ocean, which indicate a decline in oxygen. So why do we care about this, and how does it link to oxygen minimum zones? So when the ocean is losing oxygen, one of the concerns is that it will expand those areas of already very low oxygen levels. And that would have impact on ecosystems, as many microorganisms will be influenced by low oxygen levels. They can't respire, so fishes, for example. So it will impact physiology, mortality, fishing resources. Another aspect is that those areas of oxygen minimum zones are, if they expand, they would likely produce more nitrous oxide and maybe reduce the sequestration of carbon, which would have a positive feedback on climate and warming itself. Now, are they expanding or not? And so here I show a few studies, like I compile a few studies looking at those different oxygen minimum zones. And you see, for example, in the Atlantic, it seems, observations show a consistent decline in oxygen levels in that oxygen minimum zone. In the Pacific, however, it seems for the past 50 years, the oxygen levels have decreased in some places, but other studies indicate that it might be a shorter term response, and on longer timescale, like century timescale, there are indications that it might actually expand. In the Indian Ocean, the Arabian Sea, we have disparate trends depending where they are measured over the last 40 years. And if we look, like a summary of that, is those discrepancies between the different regions are probably due to those regional contrasts, but also natural variability in the system, temporal variability, which might obscure those long-term changes. But what I want to focus here is what can we learn from models, which cover a longer range and go into the future. And so here I show you a figure from the latest IPCC report 2019 on ocean and cryosphere that showed a change in ocean oxygen at those intermediate depths in those models over the historical period, which is within the observed changes, but also into the future. And if we focus on that business as usual scenario, you see a decline of about 5%. That is relatively robust across models for the global intermediate layer of the ocean. Now, however, if you look at the map of that, so here is a map of the change by 2100 in one of those business as usual model simulation, and you see where it's stippled, it means that the model agree on the sign of change, and you see they agree with or an oxygen loss in brown, in mid and high latitude, but in those oxygen minimum zones here, no stippling, which means they don't agree on the sign of change. And this is a result from the latest generation of models, which came out in 2020. And this is published by Kwiatkowski, but this is what we had already 10 years ago with the last generation of models, the semi-5 generation. And those uncertainties in the OMZ are, studies showed that they are tied to the uncertain magnitude of those biological changes and ventilation changes in those regions. It's really subtle changes, and it's really hard to get the sign of change in those models. So what I'm going to focus today is what control, I'm going to show what controls the OMZs and their volume. I'm going to talk about ventilation by the ocean circulation, those biogeochemical feedbacks. I will then give an example of the Pacific Ocean, and can we go beyond that message of the OMZ projection are uncertain using that new generation of models, and hopefully I can convince you that we can, and yes, the OMZ in the Pacific will expand according to those models. And then I'll finish with what I call the Goldilocks of OMZs is those models have very different OMZs to start with, oxygen minimums, some have small, large, and I'm going to show that the fine scale ocean circulation, how does that shape those OMZs and the implication for projections. And so I'm going to use material from several studies and published work, but I also like to acknowledge Julius was a postdoc in my group, and he's now a researcher at Columbia University, and he led a lot of the results that I'm going to show. So what controls oxygen minimum zones and their volume? So the OMZ, this is a map of the oxygen minimum zone in the Pacific, and you see in red, that's the oxygen minimum zone in the thermocline, and it's in blue are those advective pathway, the transport of the thermocline, the ventilation by the ocean circulation. And you see it's confined in what we call the shadow zone of the thermocline, where there is no direct transport by advection. If we look at the section here around 120 west as a function of depth and latitude, and you see what the OMZ here, the oxygen minimum zone cover what we call the upper thermocline here, and most of the volume is what we call the lower thermocline. So the upper thermocline is the water oxygen is supplied by the subtropical cells, those cells here, while the lower thermocline is ventilated by mode and intermediate waters. Now, what's happening in the OMZ? So in the OMZ, it's a very subtle balance, I was saying, in between the slow supply of oxygen by mixing and the biological oxygen demand by respiration, which is actually also somehow linked to mixing, because we expect with more mixing or vertical exchange, you will have more nutrients, more production, and then more oxygen demand. And so it's a subtle balance because you have that opposed effect of mixing. More mixing will increase the supply of oxygen, but it will probably also increase the oxygen demand and respiration. And that's why it's hard to model that in a very current way, because it is very sensitive to those processes. So what do we expect with warming? So as the ocean warms, we expect weaker ventilation by the large-scale circulation, the ventilation pathways, but we also expect weaker mixing, which will have opposite effects on the ventilation and the biological demand. And so we can see, we could definitely see a two outcome, one where the ventilation reduction exceeds the biogeochemical feedback, and then you will have an OMZ expansion, and one when the biogeochemical feedbacks exceed the ventilation, the reduction in ventilation, where you would have a contraction of the OMZ. And this is nicely illustrated. I'm not going to go into detail, but by that study by Dute et al. In 2011, where they show changing the mixing rates, that the ventilation wins, and so the OMZ expand if you have mixing rates that are high to start with, whereas the biogeochemical effects would win if the mixing rates are low to start with. And that gives you a hint of, depending on the molecule you're looking at, on the region you're looking at, you might have different background in mixing, and that could change the outcome. And that's why we have those uncertainties in the OMZ. Okay, but so what can we learn? What's the next step? What can we learn from that those models that we have? And we have for CMIP6, so the new model generation, we have about 16 models right now that have oxygen. And here I'm showing the structure of the Pacific oxygen minimum zone. So observation here on the left and the mean of those 16 models on the right. And this is the mean over the thermocline, the full thermocline, not like a depth slice. And you see they reproduce visually roughly the extent of the observed oxygen minimum zone, and also the extent, they also cover the upper and lower thermocline mostly. More quantitatively, if we look at the volume, you see that here you have the moles, individual moles with the little dots. You see that they span a wide range. In average, the volume in those models in average is about a third larger than the observation. But then you see you have models that have only half of the volume, and some models have more than twice the volume. So it's very variable what they simulate. Now, do they tell us a consistent picture of what's going to happen in the future, irrespective of those differences? And I think there is some messages that we can get out of that. The first here, the map that I show here is the multimodal, so it's an average of all the models of the change in the OMZ thickness. And you see that here in the OMZ region, there is an expansion. In average, they predict an expansion of 50 to 100 meters by 2100. More quantitatively, like if we look more at the volume, here I show the change in volume in average over all those models. You see that 15 out of the 16 models show that there will be an expansion of that OMZ, that it will expand by 2100, except for one, which is really close to zero. What you see also is that they span a wide range, so the magnitude is very different across models, but they all say it's going to expand. If we look a little bit more at the story between that upper thermocline and lower thermocline, we see that that expansion is controlled by the upper thermocline. And I don't know if you remember, but the volume in that upper thermocline was pretty small, but actually most of the change is happening there. And it's a consistent expansion across all the moles. Actually, they are pretty close together here. It's larger than 210 to the 15 meter cube expansion for all of them. The lower thermocline, where the bulk of the OMZ is located, however, that's where the spread comes in. And you have actually in most models, 13 out of 16, a relatively small change that is smaller than what's going on in the upper thermocline. So the upper thermocline is going to control that expansion. The lower thermocline is going to explain the spread and uncertain magnitude, I would say, between those projections. So I'm just going to go quickly about what is going on in that upper thermocline and lower thermocline. So in the upper thermocline, if I look at the oxygen chain just in that upper layer, you see a consistent oxygen loss. And here, not that hatching is now when they don't agree, but you see that in most places, models agree the oxygen is going to decline, and that's associated with an older water, so a reduction in the ventilation of those subtropical cells. And this is shown here where I plot the change in volume in those models in that layer versus an index that quantify the strengths of those subtropical cells. And you see here models with no change in the subtropical cells and almost no change in the OMZ volume. And here models that have very strong reduction in subtropical cells and those strong expansion of the OMZ volume. And this is very consistent with some model results, ocean model results that were published by Untitled in 2014. So in the upper thermocline, we are in that case where the change in ventilation exceeds the biogeochemical feedback, the OMZ is expanding. Now, what's going on in the lower thermocline? And this is the change in oxygen, again, across those models average. Hatching shows, again, when they don't agree on the sign. And you see it's a less clear signal. There are places where ventilation exceeds the biogeochemical feedback here in blue, But in the UMZ, as that's been reported before, you have either more supply by mixing or biogeochemical feedback that takes over. And that makes that balance and the uncertainty between models. And that explains the consistent projection that has been emphasized in prior work that, by the way, use the constant depth slice and not those thermocline boundaries that move with the UMZ. However, despite those uncertainties in that lower level, those effects actually yield small changes, and they modulate the magnitude of the expansion, which of course matters, but they don't really change the sign of change, the fact that the UMZ is going to expand according to all our models, except one. Okay, I'd like to finish with kind of a peek into the Goldilocks of OMZs and why, eddy circulation, that might relate to some of the things that Sören showed. So here is the panels that I showed before with observation in the World Ocean Atlas, the multimodal mean that we had, but then 3 individual models that I just picked, and one where clearly the UMZ is too small, when it's too big, and when maybe it's almost right. And I would like to briefly talk about, specifically in that equatorial portion of the UMZ, what some of the things that might explain the differences that we see. And I would like to focus on a feature that is very important for that specific equatorial band, which is the equatorial undercurrent and the alternating jets. So this is a section across here the equator. In observations in red, you have that eastward current, which is the equatorial undercurrent, and then you have those blue and red stripes off the jets, which are those alternating jets, like alternating currents. And you see here an example of a coarse, typical Earth system model, 100-kilometer resolution, where you only have a big undercurrent, but very little structure, fine-scale structure of those currents. While here you have an eddying 1/10 of a model, where you reproduce some of those alternating jets. And you see the oxygen minimum zone simulating those models will be influenced by the structure of those transport here. And I'm going to go just one slide about those differences between those two models. And here I'm showing, so it's in those two models and the observation. I'm showing a section along, the equator, the equatorial band. So this is now longitude and depth. So it's across the Pacific. Here you have South America, and here you have Southeast Asia. And I compared the observations here to that fine scale model, 10-kilometer model, to that more 100-kilometer model. What you see in the observation is that the oxygen minimum zone has a boundary, an oxycline at about 300-meter depth that extends to the Central Pacific, which is reproduced in that model. In the 1-degree model, however, it's like much more confined to the east, and it's actually much deeper, like at 500-meter, the oxycline has 500-meter depth. So it's a pretty unrealistic representation of the OMZ with very strong and low, very strong OMZ with very low oxygen levels. And an unrealistic representation of the current, which is that gray contour that kind of decelerate eastward, which is not the case in observation in the higher resolution model. And an important thing that I want to emphasize here is that the temporal variability of the oxygen minimum zone in that coarse model is 30% stronger than the eddying model, meaning its response to ENSO and climate variability, and El Nino and climate variability. And just to speak of why that is, that the structure is different, here is the ventilation budget of oxygen, what provides and supply oxygen in those models. And if we look first at those panels, which is the large scale supplied by those currents, you see that in that case, you have an equatorial undercurrent that leaks oxygen in red. It provides, and it leaks a lot of oxygen, shaving off that oxygen minimum zone, which is not the case here, where it's trapped in the upper 300 meters. Another very important thing is that mixing, which supplies oxygen to the oxygen minimum zone, is confined to the outer edge here in that case where the fine scale dynamics is not represented. Whereas it's allowed because of the representation of those fine scale structure. It goes into the OMZ core and makes a much more like uniform supply to the OMZ here. So to conclude, and some perspective, I hope that we go beyond that. We don't know what's going to happen, and I think there are some indication that our models are showing that the Pacific oxygen minimum zone will expand by 2100, and this is controlled by the upper thermocline and the subtropical cells. The magnitude of that expansion, the models indicate that it's controlled by the change in the lower thermocline, which are much more uncertain because you have a competition between those ventilation changes and those biogeochemical feedbacks in that that are much more important in the lower thermocline. Also, that competition explain the disagreements between that has been reported in prior work. And I'd like to stress the fact that they use a fixed depth, typically 100 and 600 meters, that just cut things in the middle. It's really hard to understand biologically and physically what's going on. Finally, the representation of fine scale dynamics improve the UMZ structure in our models. It also stabilizes response to climate variability, which suggests that the coarse models probably overestimate the response to climate change and that the expansion might lie in the lower estimates of our current projections. Lastly, I showed that the OMZ expansion is mostly in the upper thermocline, which is where most of the volume is in the lower thermocline, but the expansion will, in the models, is mostly in the upper thermocline, and that has a significant implication for climate feedbacks and ecosystems that live in that upper part of the ocean and the interface with the atmosphere. And that's it.
Great. Thank you very much, Laure. Very exciting talk. Questions, please ask them via the question box as usual. I start with one question or observation. You showed that there now is a robust expansion of suboxic waters in the CMAP6 models. That wasn't the case, I think, in the earlier CMAP models, or it wasn't maybe analyzed in that way. Do you think, is there anything that the new models do better or differently?
So I have not looked at the previous generation in that framework, but there are two things. Looking at them with just the depth slice is just, it's really hard to follow what's going on specifically when you look at ventilation effect if you take 100 to 600 meters, for example. So there might be something similar in the previous generation. However, what is very different in that new generation is some of those jets, for example, and those finer scale things, dynamics, are actually now, some of it is present in that new generation. And I think we probably have more stable OMZs in the new generation that we had in the previous generation.
Yes, okay, thanks. And there's a question by Eric Machu, maybe connected, is, do any of the CMAP6 models take into account possible variations in carbon to nitrogen ratios and the drawdown and fertilization effects?
Yeah, so the biogeochemical models are very different across the different models. Today I talked mostly about the respiration feedback, but actually some of them have denitrification, which will be more important for like the very like suboxic, like the very low oxygen waters, but not all models have denitrification. Some of them have deposition from the atmosphere, some don't. Some of them have variable carbon to nitrogen ratio, although it's really not the majority of them don't.
Do you see any systematic difference among those that do include it? No. Okay. So
I haven't looked at that in that framework, although we are digging a little bit more in those biogeochemical feedback right now. It's always more messy when you look at biogeochemical feedbacks, yeah. But we're looking into it. Yes.
Thanks. The question by Yard Hauschild. what role do possible biases in the mixing, subgrid scale mixing, introduce, and how could it affect the future evolution of oxygen minimum zones?
Yeah, so I think that's a very interesting question. So there are many studies out there that show that when you change the mixing, you change the outcome. When you change the background mixing, I mean, your group, Andreas, has done a lot of that. Nanodesican group has done a lot of that. What we show here, comparing those two models that are exactly, the same model except for that resolution, one is resolving some of that mixing, AD mixing, whereas the other is fully parameterized. What we see is it changes the shape and the structure of the UMZ, but it will also change what I think is very interesting, its response to climate variability. Because it seems those structure make it, at least in the Pacific, make it more stable. Those AD structure make it more stable and less prone to change. And I think that might impact the projection. And we see that in the new generation, the one that have more of those finer scale that are 1/4 degree versus, more, they actually show usually less change than the other ones. So I think it's starting to emerge something along those lines, that representing better those fine scale AD mixing structure will stabilize the UMZ and maybe have less extreme changes in their projection.
And is this mostly via the zonal currents or also via vertical processes?
That example was really equatorial. Obviously, it's mostly the equatorial, and that's an example. I don't know. I haven't looked, how that would impact really the flank in the subtropical area, but at least in the equatorial band, which is the biggest band of UMZ, that's what's happening.
Yes. Okay. Then another question, or a few questions about marine biogeochemistry. One by Diana Respino. Is the denitrification, representation of denitrification, the models, that's often different? Does it matter in the end for the evolution of oxygen and deoxygenation?
Yes, so some models have denitrification, but basically the respiration feedback that I've talked about, as you decrease mixing, it's gonna reduce productivity, reduce biological demand. Denitrification will have, so it's kind of a negative feedback, whereas a positive feedback, whereas, sorry, I'm confused. It's going to decrease the amount of respiration. Denitrification will have the opposed feedback, meaning when you reduce mixing, you will reduce the amount of nutrients and reduce the amount of export, allowing more respiration and less denitrification. So that wasn't very clear, I'm sorry. But respiration feedback and denitrification feedback goes, in opposed way. But the denitrification will be mostly in those very low waters, oxygen waters, which are not very well represented in those models to start with, which is why I looked mostly at 80 micromolar volumes here.
And same probably applies to phosphorus release or iron release from sediments, which could induce there. And then one final question, since we're running out of time, unfortunately, about mixing parameterizations in models. Have you found any that you would recommend for the next generation of CMIP models? If we would concentrate only on the oxygenation.
So some results show that having, less to have non-homogeneous parameterization doesn't really, in the current framework that we have, doesn't really make a huge difference. If you change the value of the mixing, yes, it does make a difference, but making it more like anisotropic or something like that doesn't seem to make major differences. I would say, to me, what the models that looks better are the one that actually start to resolve some of the scale. I'm not talking about sub-mesoscale. I'm talking just, some of those features, a 1/4 degree or something like that. They look more realistic to me, the simulations that have those features.
Okay. Thank you very much, Laure. Very exciting talk, exciting question and answer session. And we have many more questions here. We will send them all to you, and you will find out how many of them you can answer and feedback to the audience. Thanks to all of you, to the audience, to fantastic speakers today, and I'm glad this webinar is receiving so much attention and yeah, very, very forward-looking presentations. I think really showing scientific progress we are making currently. We have a next webinar, the third one coming up next year, 20th of January. We will have Laure from Chile and Christopher Gobler from Stony Brook. And we also invite everybody, every one of you to, if you have an interesting topic, talk you want to present here, there's in the chat right now the link for where you can submit abstracts of your presentation. So we hope to continue this well for much longer than the COVID pandemic will go on, and have use this as a contact point for exciting oxygen research. So please submit your abstract there, and you can also find it on the website soon, where we will also then publish the recording of today's lectures. Unless you have any objections, then let us know, we cut it out. And I all wish you well, quite calm, particularly healthy Christmas, New Year season, and hope to see you all back first virtually in January, and then hopefully in the real world again soon next year and thereafter. Stay healthy. Thanks to all of you, to the organizers, Kirsten Isense, Chris Shelton, Marie-Laure Gregoire, and the entire team of the GO2NE Global Ocean Oxygen Network, and all of you scientists, early career, later career scientists, to make this happen. And I hope we all had a fruitful exchange. Thanks very much, and see you soon. Goodbye.
Bye.
Mm.